We introduce DragView, a novel and interactive framework for generating novel views of unseen scenes. DragView initializes the new view from a single source image, and the rendering is supported by a sparse set of unposed multi-view images, all seamlessly executed within a single feed-forward pass. Numerous efforts have been exerted to diminish the necessity for calibrated camera poses before generating novel views. For example, BARF assume the multi-view images are calibrated with noise poses. The neural radiance field and poses are jointly optimized in training. However, BARF is a method that requires per-scene optimization, which is time-consuming. Scene Representation Transformer or SRT has expanded the ability to process multiple images as a set latent scene representation and generate novel views even in the presence of flawed camera poses or without any pose information. However, the latent representation results in blurred rendering outcomes with a lower resolution, for example 176 by 128, limiting their applicability in achieving photorealistic rendering. Single View Method, Pixel Nerf, bypass the demand for camera poses by adopting only a single image to learn generalizable nerfs, and render the target image from the constructed feature volume. However, the problem of scene reconstruction under a single input is highly ill-posed and faces challenges in the wild scenes. In this work, we tackle the problem of generalizable novel view synthesis with unposed images from a fresh perspective. We propose to leverage pixel-aligned features for each target pixel, and incorporate image-based rendering to warp and composite source images into target view in a learnable manner. Inspired by previous works, which search the potential source pixels used for blending along the epipolar line, with known camera poses, we propose to use such powerful learnable representation for novel view synthesis. However, under such unposed setting, epipolar line cannot be explicitly constructed. Therefore, we propose to utilize a relative coordinate system, and broaden the epipolar attention mechanism to encompass all source pixels. The first challenge is how to build such relative coordinate system. We contend that selecting a source view, named as starting view, as the initial viewpoint and enabling users to interactively explore the target view is more realistic. Consequently, users initially start from one of the source images and drag it through the mouse or the VR headset to specify the target view for rendering. Then a ray is shot for each target pixel and discrete 3D points are sampled along the ray. The initialization of the pixel-aligned 3D features is achieved by projecting the 3D points onto the source view, by establishing a local relative transformation between the user-controlled target view and a user-selected source view. The most direct method for aggregating the 3D point-wise feature is by introducing a tension mechanism that works between the 3D points and all source pixels. However, this is proved to be intractable as the attention complexity will be quadratic to the token number. During each iteration, the sampled ray is typically large, for example, 4096, incurring 4096 by 128 sampled points in each iteration. The number of source pixels is also very huge. We therefore propose to extract the multi-scale 2D features from the source view images, and tokenizing each view by subdividing into M by M patch grids. Having these tokenized patches, we propose the intraview attention which perform intra-image long-range global context aggregation can retrieve relevant information within the given view. Then, akin to the class token in Vision Transformer, we propose the interview attention are performed separately to capture cross-relationships across these two views, and inter-image feature interaction between images toward the starting view is done in this way. We then project the sampled 3D points onto the starting view, ensuring an efficient implementation regardless of the number of source views used. Subsequently, a feature-wise linear modulation is utilized to scale and shift the point feature, to handle the occluded or missed projections. A ray-wise attention module is applied to determine the aggregation weights for each sampled point feature, further decoding into pixel intensities in a learnable fashion. During the training phase, a view selector is designed to select the nearest K source images from the N unposed source images. During inference, with the designed framework, DragView can render high-resolution and photo-realistic new viewpoints, in a single feed-forward pass. During the rendering stage, we do not assume any posed images. All images are rendered controlled by user's mouse or headset. Compared with multi-view method, SRT, and single-view method, Pixel Nerf, wherein it can be observed that the latent representation in SRT overlooks the image details, and Pixel Nerf struggles under complex scenes using single-view feature volume-based neural rendering. This validates that drag view not only leverages the information within the starting view but also effectively aggregates pixel-aligned features from unposed source views. Multi-view images captured in the real world typically necessitate a pre-processing step to compute the poses, for example CowMap. However, the computation is slow, especially when the number of source images is large, and it often contains errors. We examine the current best-performing generalizable nerfs against noisy camera poses in the tested source views, a practical concern. We apply additive Gaussian perturbation on source images of a new scene. All generalizable methods suffer from noisy camera poses, with significant degradation in performance even under a small amount of noisy calibration. Drag view, which generates new views in a feed-forward pass without estimating camera poses, demonstrates stability in the rendering quality. Drag view, which generates new views in a feed-forward pass without estimating camera poses, demonstrates stability in the rendering quality.